Hi friends, welcome back to my channel on statistics. If you are seeing my videos first time, then do subscribe. Let's go to the topic. In the before videos regarding to the statistical inference, I explained about what is statistical inference and types and what are the ideal properties of best estimator. And quick overview also done about ideal estimators. In this video, I will highly explain on unbiasedness. In the before video, I explained about what is unbiasedness with examples also. What unbiasedness? If any for any test statistic, expected value of test statistics means sample statistic equal to the population parameter. Then we can say that it is unbiased estimator. If not equal to, then we can say that biased estimator. We done lot of examples also from binomial, Poisson, exponential, normal distributions, all distributions also. In this video I will explain mainly how many ways we can explain about unbiasedness. How many methods? See, how many methods for finding unbiased estimator. Sometimes unbiased estimator does not exist. Sometimes it will be observed. Sometimes it will not give exact results also. All things we can see with examples also. And uniformly minimum variance, locally minimum variance, and mean square error also explain in this video. From next video I will explain about CR Kramer-Rao lower bound. Okay, now let's go to the example. See, this is my example one. I prefer for statistical inference, first you can read fundamentals of mathematical statistics book, then introduction to probability theory by J.K. Rothke book. This example also from Rothke book. See example. Let x1, x2 and so on xn be a random sample from some population with finite means. Means our samples x1 up to xn from finite population. Then x bar is unbiased for the population. We know that if you take one example, first you can read, if the population variance is finite, then the sample variance s square is unbiased for the population variance in general. If the kth population movement mk exists, then the kth sample movement is unbiased for mk. This is question mark. Now we can check. In general, you can take any example. For example, you can take normal distribution. In normal distribution, what x bar is unbiased for mu. X bar is unbiased for mu. We know this. And what about sigma square? Sigma square is unbiased for sam. See, sigma square is not unbiased for sam. See, sorry. S square is unbiased for sigma square. Where S square is what? S square means 1 upon n minus 1. In general, it is not unbiased. When you can take sampling variance, it is then unbiased for sigma square. You can, this result also follows what? N minus 1 into S square divides sigma square. This distribution follows chi square with n minus 1 degrees of freedom. We know this. Chi square n minus 1 degrees of freedom. Okay. Now what is question? We know that x bar is unbiased, then sample variance also unbiased for this is for chi square distribution with n minus 1 degrees of freedom. Now question is, in general, if the kth population movement mk exists, then the kth sample is unbiased for mk or not. For checking what we need, for this we need find the expected value of this. Expected value of s into root n minus 1 divides sigma. Okay. Expected value of sample variance divides population variance into square root of n minus 1. When you can solve this derivation by taking chi square integral starts from 0 to infinity. It is not bell shaped curve. We all are not. You can apply chi square PDF. Then finally you got expected value for this question is expected value of sample variance standard deviation equal to sigma 2 upon n minus 1. When you can solve the derivation of chi-square, then you get this result into gamma of n by 2 gamma of n by 2 gamma of n minus 1 something. You get this. Finally you got biased estimator. When n increases means asymptotically it will goes to the unbiased for sigma. It is not this, generally it is not unbiased for sigma square, asymptotically unbiased for sigma population variance. Okay, now this is one example for, this is also one method of unbiased estimator. Now we can see another method. See, this is an unbiased estimator does not always exist, means if sometimes unbiased estimator also not exist. If we take example, this is example related to the binomial distribution. See, consider a random variable with PMF Bernoulli, means here I am taking Bernoulli. Suppose we wish to estimate, this is my test statistic, then order T is unbiased for P square. See, for checking this, if you take, what was our question assumption, I am taking T of P, anything you can take equal to Pn plus 1. Okay, then what is unbiased expected value of this statistic equal to the P of P power n plus 1. When this condition satisfied, then we can say that unbiasedness. Now we can check it is satisfied or not satisfied. For checking this, what result we need means summation x equal to 0 to n tx. This is test static, I am taking TP. Then we can write PMF of binomial distribution. Then this results will be equal to the probability of P power n plus 1. When you observe this equation, it is not equal to the P power n plus 1. You can solve all equations and all derivations also. This will be not true in general, so it is unbiased estimator for P square is not exist. This is a simple example. You can take other examples also, you can refer some books. Okay, now we can see some examples. See, sometimes an unbiased estimator may be observed, means if you observe this example, then you can understand. See what this says, that x follows Poisson distribution with parameter lambda. This is clear. Then what this say, test statistics e power minus 3 lambda, then we show that T of x is unbiased. See what this say, now we need to find expected value of minus 2 whole power x equal to 2 whole power x equal to e power minus 3 lambda. We need this result. Okay, we need to show that this, when this condition satisfied, then we say that our test statistic is unbiasedness. For checking this, what we need, now we need expected value of e power minus 2x, means summation Poisson variance start from 0 to infinity, x equal to 0 to infinity, then what, minus 2 power x. If x is there, we can write x. If minus 2 power x is there, we can write minus 2 power x. You know that PMF e power minus lambda power x divides x factorial. Here x varies from 0 to infinity. Here e power minus lambda is constant. Okay, e power minus lambda is constant. It will come outside. E power minus lambda is constant. Okay, when you observe this expression, lambda power x divided by x factorial, lambda power x divides by x factorial, it multiplied by minus 2 power x. Okay, x equal to 0 to infinity. What is condition? Minus 2 lambda power x divides x factorial. Divides x factorial. When you solve this expression, you got e power minus 3 lambda. You got this expression goes to e exponential power minus 2 lambda. This is exponential minus. Finally, you got exponential minus 3 lambda. Here you got unbiased estimator, but how you got unbiased estimator means here minus 2 power x is always greater than 0. Okay, if x is even and less than 0, if x is odd, it is observed. Yeah, okay, if you understand this example, this is not possible for all cases. When e power minus 2 power x is even, then it will be greater than 0. When it will be odd, then it will be less than 0. That time you can difficult to tell results. Okay, thank you. Now we can see these examples. Unbiased estimator exceeds infinitely. Unbiased estimators exceed. This is the example related to the infinite unbiased estimators for it. See, let x1, x2 and xk be a sample from Poisson lambda here. Then x bar is unbiased from lambda. So, and also s square also. In Poisson distribution, x bar and square both are unbiased estimator for lambda. Since both the mean and variance are equal to lambda, indeed this is the convex function, convex set. When convex set exists, then we can say that it has infinite unbiased estimators. What we say, infinite unbiased estimators. When you observe these equations also, you can understand when convex set exists or one-to-one functions are exist, then it has infinite number of unbiased estimators. Okay, now we can see what is locally minimum variance unbiased estimator and uniformly minimum variance unbiased estimators. See what is locally. Let theta naught belongs to the capital theta and mu theta naught is the class of unbiased estimators t of theta such that this is what second central moment it less than infinity, then t naught belongs to mu theta is called local. This is condition we need to satisfy. This is important. Expected value of t minus theta whole square less than or equal to, see, this is expected value of test statistic minus theta whole square less than or equal to expected value of here, this is another test statistics t minus theta whole square. Then we can say that it is locally minimum variance unbiased estimator. When we can say that uniformly minimum variance unbiased estimator means we need to satisfy this condition. Here for all theta is there, here for all theta is not there. This is important. Okay, when this value belongs to each and every capital pi, then we can say that it is uniformly minimum. It is not equal to, then we can say that minimum variance unbiased estimators. Now we can see some theorems also related to the uniformly minimum variance estimators and locally. Let me be this result, direct results. You can, for proof, you can refer book also, this book. Okay, this is also some theorems related to the UMVUE and locally minimum variance. By observing the examples, you can understand what is uniformly minimum variance unbiased estimators and uniformly local minimum variance unbiased. Now we can go to the examples. See, this is the example. Let x1, x2 and so on xn be IID Poisson lambda values. Here x bar is the uniformly minimum variance unbiased from lambda. Surely x bar is unbiased and g be unbiased estimator of g. This is condition for completeness. We can see, we know that what is condition for x complete for finding complete statistic. This is the condition for complete distribution. When it will satisfy, then we can say that it is complete. This distribution is complete. Here by observing the that above theorem results, we can say that it is uniformly minimum variance unbiased estimator for lambda. Okay, now we can see another example also. See, this is theorem related to the, see, if a sample consists of an independent observation extended from the same distribution, then the UMV exit is symmetry function of exit. This result is important. You can refer from books also. Okay, you can refer from this book. You can see some more examples also. See, let what do you say? Let x1, x2 and so on xn be IID Bernoulli random variables. Then this is our complete substance statistics. We know this is complete substance statistics. How you know that this is complete substance statistics? When you can write NCX, when you can write joint probabilities NCX p power x q power n minus x. This is binomial PMF. When you write joint probabilities, that time you get summation AXI. When you get summation XI, this gives the complete information about probability. So it is sufficient estimator and complete sufficient estimator also. Then UMVE of P is clearly X bar. How we can say that it is UMVE? It will satisfy the conditions also. To find the, see, this is conditions. P here UMVE for P is X bar. Then we need to find the P into 1 minus means P minus P square. UMVE is what? This is the UMVE for P minus P square. Nt minus T square divides by N into N minus. Here T is sum of X values. This is also one example related to the normal distribution. You can observe it. You can understand this also. These all examples from Rothke book. For more examples, you can refer Rothke book. From the next video onwards, I will explain about Sierra inequalities. Sorry, Sierra lower bound theorem with examples. After that, I will give you lot of examples from unbiasedness. Thank you.